Hello guys, so I will continue our discussion on data reduction techniques, theory and practice. This is the second and the continuation video, part 1, and in this session we will cover deduplication internals and touch on some of the fundamental problems associated with deduplication systems. Later we will also cover some of the well-known workarounds for these problems. We will talk about pros and cons with each option. Here is the outline of this video series. Again, in this session, we will focus more on chunking and indexing issues and mention a few known problems such as this bottleneck problem and also provide some workarounds. Finally, we will touch upon collisions and resolutions. Particularly, we will investigate the effect of collisions on a file and talk about workarounds in general and mention a few implementation details. Okay, so if you remember our previous discussions in the previous video, subfile deduplication involves chunking the given file based on fixed or variable length operation. This is particularly effective if you would like to get good compression performance. As you might guess, fixed length chunking is fast and easy, but not very effective because of boundary shifting problem. Even if we insert or delete a byte, then it affects all the data following it, and duplicates cannot be detected in that case. So there are two desirable properties for chunking. First is called the stability property. In other words, even if we have local changes to the file, most of the boundary locations must stay the same. The second desirable property is called statelessness. So to say, the chunking algorithm must produce the same set of chunks no matter where and when it's run. So the chunking algorithm will be applicable to source and target and inline and post-process deduplications and produce the very same result in each of these cases. One of the simplest methods to make chunking operations stable under local changes to the file is to use variable size chunks. In other words, we allow chunk sizes to be variable and find boundaries in a way that when a small modification takes place, most of the chunk boundaries stays the same under linear shifts. One of the well-known variable length chunking algorithm is called sliding windowing technique. In this technique, we set integers r and d such that r is strictly less than d. These are parameters of the algorithm. We also define a fingerprinting function or a hash function, usually low complexity, such as Rabin, and we slide a window of some size over the sequence of symbols. For each shift of the window, we compute a hash-based number on the contents based on the contents of the window modulo d. In the case the result of this computation equals r, then we claim we hit a boundary. In most of the practical cases, people choose r to be equal to d minus 1. However, these selections are quite application dependent, and what's important is that sliding a window, computing a number, and checking if it equals to some predefined number are the sub-operations of the boundary detection problem. At the end of this procedure, we will have variable size chunks defined by the chunk boundaries. And we can verify that mathematically a small modification to a file when we rerun the SWT algorithm, this will lead to big first affected chunk. In other words, the first affected chunk will turn out to be a large chunk, and that eventually increases the amount of information to store or transmit depending on what your application is. On the other hand, zero chunk size variation, in other words, fixed length chunks, increases the number of affected chunks. In effect, all the chunks that comes right after the first affected chunk. Plus, fixed size chunking violates the stability criterion. So we need a trade-off. In other words, we need an algorithm that will minimize both the number of affected chunks as well as the chunk size variance jointly. To be able to reduce the variance, we can merge small chunks. And one way of doing it, we can ignore fingerprint or hash value that are matched before a threshold L is reached. The optimal L depends on the choice of V. second and complementary approach is to break the large chunks. One way of doing it is to break all the chunks that are bigger than, let's say, t into as many length t chunks as possible. However, we notice that, similar to fixed size chunking, this method suffers from the offset problem for as long as the number of fixed length chunks. An advanced workaround to this is to use two integers, d and d prime, and d prime is strictly less than d. The idea is that we check boundaries based on both of these integers. Instead of on single one letter, now we have got two variables, d prime and d. And if d prime divides d, then we will have more boundaries found based on d prime than d. And moreover, the set of boundaries generated due to d will be a subset of the set of boundaries generated due to d prime. Therefore, if a large chunk is produced, we will fall back to the most recent boundary found due to d prime. This method does not produce fixed size chunks, as you might guess, and it is used along with chunk merging mentioned earlier to make up the principles of an algorithm called two-threshold, two-divisor algorithm, which is also known as TTTD, triple TD algorithm. In order to reduce the computation overhead of triple TD algorithm, an average of L and T can be used. Once the continuous scan reaches that value, d over 2 and d prime over 2 are used until a breakpoint is found. So I'm trying to skip the details of this algorithm as the time will not allow us to, cover all the topics that we are supposed to cover with this video. So more information about this interesting algorithm can be found at the reference down below. I also included that reference at the very end of the slides. Next, let us consider the indexing problem. Indexes or hashes or fingerprints, they're all, synonymous with each other, are nothing but identifiers for chunks as introduced earlier. These are stored in an index table that is preferably living on a random access memory because it's fast. In a typical deduplication system, when a new chunk arrives, its fingerprint must be first computed and then compared with the index entries to decide whether it's a new chunk or a duplicate one. One of the problems with data duplication system is to rapidly identify duplicate items across index table without sacrificing performance, scalability, and resource efficiency. Indexing is a popular subject matter of computer science, and there are three based algorithms that decreases the search problem to O log n time, as you might be already familiar, which is way better than ON. For large values of n. As you might guess, by the way, as n increases, it becomes difficult to hold the entire chunk index inside the main memory because it gets huge and it will probably not fit into your RAM, physical RAM. What happens is that the part that does not fit will automatically be paged to the disk, which has a slower I/O. So this means we need to initiate I/O with the disk subsystem, which will get list, 10, maybe more than 10, maybe 20x more time. It'll take more time to access data, write, read the data compared to RAM accesses. So this gap in performance creates latency issues with the deduplication system, which is known as disk bottleneck problem. So I want to talk about, one of the most popular methods in literature called Bloom filters that is used, they are used for determining set memberships. Bloom filters are widely used in deduplication systems and has many applications, in different systems, such as firewall blocking or string search, etc. That asks for membership queries. So that's the application area where Bloom filters are useful. The way we use it for our application involves finding whether a given chunk belongs to the index table we keep on RAM. Instead of comparing indexes one by one, which might be time consuming, it might be preferable to devise a method that can tell with high probability if a given index is already included in the index table. So here's a more formal definition of Bloom filters. Let X be an element and S be a set of elements, so the algorithm's objective is to determine whether X is an element of S. given x and s are inputs. The output is either true or false if x is in S or not, respectively. The beauty of Bloom filter is that it determines the set membership very, very efficiently, of course at the expense of some errors. There are two error cases. The first is called, false positive. This happens when the output is true while x is not in S. This can happen in Bloom filters. Second case is false negative. In other words, the output is false while x is actually in S. We will see that the second case never happens. In other words, if S is in S, Bloom filter always returns true. So let us explore the details of the algorithm. We use an array of Boolean values where each entry is set to false initially. Here I show you an example with n equals 10. So there are 10 entries, 10 cells to illustrate the idea, but in general n is much, much larger. Next, we consider k distinct hash functions. Then we fill the array entries by looking at each member of the set, apply hash functions, and find the corresponding position in the array, and turn the entry to true. A particular Boolean value can be set to true multiple times, but it does not matter how many times it's turned to true. Once it turns to true, it maintains that state. Once we're done with this phase, the Boolean array is ready to use for comparisons. An example is shown at the bottom of the slide where the set has 3 elements and we use 2 hash functions. The yellow entry is turned true due to hash mappings land on them. So when you have another file like S4 and then we compute the 2 hash functions, based on that output of these 2 hash functions, we determine whether S4 belongs to the set S or not, and hopefully it will not belong to S. Okay, so by now we might have guessed the decision rule here. For a new element x, we compute the true locations and finally check with the Boolean array if the locations are already true. If so, we say x is in S. Otherwise, we say x not in S. So notice that if x is in S, we surely find it because we use the same set of hash functions every time. That's why we don't have false negative. If x is not in S, we may accidentally find all locations true due to other elements in the set, so we have some probability of false positive. So a major task here is to quantify this probability and choose an appropriate n, the length of the array, for it. Let us start with a simple assumption about hash functions. We assume they produce any of the array entries with equal likely probability. This is quite valid for strong hashing, and we will basically cover the ideal hashing later. So look up on web if you want to have more information. Look up on the web for more information about the ideal hashing and the hash functions that have that property. Then the probability that a particular entry stays false after all hash functions of all m elements make selections is approximately exponential raised to the power minus km over n. So for a new element x to be misdecided, we gotta have each k locations true. So the question is, what is the probability of this happening? Using union type bound, we can determine it to be less than 1 minus exponential raised to the power minus km over n, and the whole thing is raised to the power k. So that is our upper bound. So the parameter m, the number of elements in the set, is usually given. In our application, for instance, it could be the number of unique chunks in a deduplication system. So I'm trying to draw parallels between our application and the parameters that make up this algorithm work. Consider the upper bound we derived earlier. If you take derivative and set it equal to 0 with respect to k, you can find the optimal number of hash functions k to be equal to natural log of 2 multiplied by n over m. So let us call this k star. So the false positive probability is given by 2 raised to the power log 2n over m. From here we can isolate n over m as shown. Therefore, for a given target false positive rate or probability bound, such as 1 every 1,000, or let's say, we can figure the relationship between the number of unique chunks in the system and the size of the Boolean array that we should keep to be able to meet the error target. So Bloom filters are extremely fast, particularly when the number of unique chunks are large, which is typical in today's big data centers. I also want to talk about widely used technique for mapping data chunks to indexes. Remember that hashing is one of the ways of performing this mapping as shown here in the slide. And there are also other ways, but here hashing is the most common, most natural way of doing it. Hashing is a function that maps the contents of the chunk to some number. In a key value context, you can think of chunk contents as being keys to our system, and indexes are values. Hash indexes are used to compare various chunks to decide whether they're identical copy or distinct copies. One of the questions you might ask, since the number of bits used to represent chunks are very less than the original size of the chunk, there might be a representation problem here. One of the outcomes of such is called hash collisions. In other words, we may use a hash function such that two different chunks may end up having the same index. So this follows from the pigeonhole principle from discrete mathematics. So it's of interest to compute what the probability of collision is in a given system setting. Okay, so to be able to do that, let us start with the concept of ideal hashing. This is a theoretical assumption about the hash functions, and all practical strong hash functions resemble the theoretical behavior. So it's a very useful method and assumption, and most of the time it's a very valid assumption in practical applications, unless the hash function is designed unbalanced for a particular reason. In ideal hash mapping, is a perfectly balanced hashing algorithm. So let m be the number of chunks and n be the number of entries in the index table. As we mentioned earlier, if m is greater than n, collision is certain by pigeonhole principle. In other words, the probability of collision is 1. We define the load factor to be the average number of chunks falling onto the same hash value. In other words, it's the actual average number of the collided indexes. So if m is less than n, we would like the practical good hash function to have load factor close to 1. In other words, low collision probability. In case of m is less than n, again, if we knew which entries of the index table are filled, we would certainly have 0 collision probability because we would have never chosen an index that's already assigned, right? However, we do not have a priori information about the mapping of these indexes. So an ideal mapping or an ideal hash function chooses indexes randomly among all possible table entries. This way, we hope to minimize the load factor. Let us see if we can calculate explicitly the collision probability. Let P sub C be the probability that at least one entry has load factor greater than 1. This probability can be calculated by first calculating the probability that you randomly map m chunks to n indexes and no collision happens. And it's given by the whole big expression on the right. The solution to this is basically already given by the classical birthday problem. If you just type it on the Google, and you will find a lot of information about birthday problem and maybe extended birthday problems. Finally, if you subtract this quantity from 1, you obtain P sub C. Furthermore, if you approximate 1 minus I over n, actually the I over n part, to be an exponential function raised to minus I over n, you can further write down the collision probability in a near closed form expression as shown to the right. Note that if m is way less than n, which was our primary assumption, the exponential assumption now becomes quite accurate. By way of illustration, I'd like to give you a real-world example where you have a target collision probability, say 10 to the minus 6. So then we can use the formula derived earlier to find the maximum number of chunks that can be used without violating the target collision probability. We plot the results where x-axis shows the number of bits used to identify indexes. In other words, if we use L bits, then n equals 2 to the L. Then y-axis also shows the log 10 of the number of chunks. We have the bold straight line, is being the upper bound on the number of chunks that can be represented with collision probability less than or equal to the target collision probability 10 to the minus 6. You can carry out the same calculation, same reasoning for other target collision probabilities like 10 to the minus 16 I shown you here, 10 to the minus 26, 10 to the minus 36. As you lower the target, you can realize that you need more bits for indexes to be able to allow a reasonable number of chunks that can be represented without any problems. Besides the collision probability, it's extremely useful in hash-based deduplication systems to quantify the damage these collisions create on files. So let us look at the example. We have a bunch of chunks painted different colors on top, and after deduplication, suppose that the light and dark blue chunks share the same index due to hash collision. And as a result, we obtain the set of unique chunks shown right below the top picture. The arrows show the mapping between the chunks and the corresponding base chunk or indexes. These chunks are the ones that are actually stored. I'm talking about the chunk stream in the middle. The dark blue is lost again due to collision phenomenon. Once we want to reconstruct the data, we get a file shown at the bottom, which is smaller than the original because the light blue chunk now replaces the bigger dark blue chunk by the reconstruction procedure. So it's of interest to quantify on average how harmful this would be from reconstruction point of view. Final goal with this little discussion is to quantify how much of an effect this creates on the loading factor, because we will talk about workarounds for problems, and it's always good to keep the load factor close to 1. So fortunately, it's not too hard to quantify the damage for a given n unique chunk sizes of which can be varied between tmin, tmax. I'm assuming that I'm using triple TD algorithm. The average number of collided chunks is given by ANCC, which is given by n minus 2 to the L, multiplied by, in parentheses, 1 minus exponential raised to the power 1 minus n 2 to the minus L. So which is a good approximation for L, way greater than log 2n. And this can be proved easily by defining indicator functions and expectation calculations, but I'll skip the details here, and I put the proof in the references, and then I'll move to discuss the effect on the loading factor. If you're interested, I urge you to go to the reference that I'll mention later and look at the proof there. As you might guess, the minimum effect would be generated if the average number of collided chunks is distributed over all the index possibilities, which is 2 to the minus 2 to the L. And this actually happens for ideal hashing, so the average loading factor should not be too far from 1 minus ANCC divided by 2 to the L. As you can imagine from this expression, that for large L, we will have average loading factor getting close to 1. And notice that large L means large capital N, which again boils down to the assumption that capital N is way greater than capital N, which was our primary assumption. Here is a plot showing the average number of collided chunks as a function of number of bits L to represent indexes. We have drawn it for different number of unique chunks. So for a given number L bits, as the number of unique chunks increase, the average number of collided chunks increases also, so which is an expected result. Finally, I'd like to slightly touch upon a common solution that is used to resolve hash collisions in the deduplication context. This method is known as separate chaining, and there are also other methods, based on different techniques. And this technique, separate chaining, is based on linked lists. The idea here is to keep a list of all elements that hash to the same value. In the example below, we show 4 chunks actually mapping to the same index, and indexes become pointers to the corresponding linked lists. If there are 4 chunking, mapped to the same index, as is the case with this example, then we have a 4-element linked list. I'm assuming here that you are familiar with data structures like linked lists. Note that the average search window here is given by the average load factor. Insertion and deletions are quite easy with this method, as all it takes to insert or delete is to put the data at the appropriate positions in the linked list and change the pointers. The downside of separate chaining is the extra space consumption to hold the linked lists, right? And as you can see, we can design the load factor to play with the size of the search window and be able to trade off the space and computation efficiency of the overall deduplication system. So these are all trade-offs that a designer should make decisions, and based on these parameters, the designer has to make some choices. There are also other alternative methods, as I said, that use less memory space for handling collisions, but it's just beyond the scope of today's presentation. All right, so I'd like to end my talk here, and here are the references for the content we covered in this session. The one at the end is where you can find proofs about probability calculations in hashing, and we skipped, for instance, the average number of collided chunks earlier, so you can find arguments, proofs in that reference. Furthermore, you can find more information about sliding windowing technique, triple TD algorithm, which is the first two references, I assume, and there's also Bloom filter reference, which is the third reference. So I hope you enjoyed the video. See you next time.